Hello and Assalamu alaikum everybody. This lecture is about second order systems. Overall, we'll be looking into the time domain analysis of second order systems. In the previous lectures, we have discussed lots of things about the first order systems, such as finding poles and zeros of the first order system and the transient and the steady state response. Now, compared to the simplicity of the first order system, a second order system can exhibit a wide range of responses, so we should be able to analyze how a second order system behaves. In first order system, we were simply playing with the parameters T and K. T was the time constant and K was the DC gain, and simply by changing these two parameters we were able to change the speed and offset of the system response. As compared to the first order system, in a second order system, changing certain parameters can change the overall response of the system. A second order system can display characteristics much like a first order system. However, depending on the component values, it can exhibit a damped response or a pure oscillation-like response for its transient state. This is the generic form of a second order system, which is given by its transfer function. The transfer function is C of S divided by R of S is equals to omega n square divided by S square plus 2 zeta omega n of S plus omega n square. This is the generic, this is the transfer function of a second order system. If we want to draw this transfer function in the form of a block diagram, then you can see it is given here. So this is our feed forward transfer function, and the feedback element is just unity. So if you solve this block diagram, you will come up with this second order transfer function equation. In this transfer function, we have omega of n, which is the undamped natural frequency. This is the frequency of oscillation of the system without any damping. Or in other words, we can say that this is the frequency at which your system is operating. Then we have zeta, which is the damping ratio. Zeta can be defined as the measure of degree of resistance to change in the system output. We'll define this parameter in the later slides. Okay, so let us just solve one example related to the transfer function of a second order system. You have this equation, that is C of S upon R of S is equals to 4 divided by S square plus 2S plus 4. Now, we want to find out the values of omega n and zeta from this transfer function. So the first thing that you have to do is to compare this transfer function with the generic form of a second order system transfer function, which is given here. So after comparing these two equations, we can say that omega n square is equals to 4. So taking under root, we can find out omega n equals to 2 radians per second. Now, if we compare the second term of this equation with the generic form, we can say that 2 zeta omega n of S is equals to 2 of S. So if we cancel out S from both of these sides, we'll be left with only zeta omega n is equals to 1. Now we have already find out the value of omega n, which is 2. If we put this value of omega n here, we can find out zeta equals to 0.5. Okay. Now in the next part we would like to find out the poles of this second order transfer function. So the poles are usually find out from the denominator of a transfer function. The denominator is s square plus 2 zeta omega n of s plus omega n square. So you can simply factorize this equation, or otherwise you can also apply quadratic formula. I have applied quadratic formula to find out the poles of the system, which are minus omega n zeta plus omega n under root zeta square minus 1, and then another pole minus omega n zeta minus omega n under root zeta square minus 1. Now the zeta here in these two poles, it is a very important part, because based on the value of zeta we can categorize a second order system into 4 different sections. Now if the value of zeta is greater than 1, then we'll say the system that we are dealing with is an overdamped system. In this case, if you put the values of zeta in this equation, you will always come up with 2 real poles on the S plane, that is here. So after putting zeta greater than 1, we will come up with 2 poles on the negative real axis, 2 different poles. The second case is if the value of zeta is between 0 and 1. In that case, we'll say the system that we are dealing with is an overdamped system. After putting the value of zeta between 0 and 1, any value between 0 and 1 in this equation, we will always get complex conjugate poles, which you can draw on the S plane like this. 1 pole here and 1 pole here. Say for example, let us just put in this equation zeta is equals to 0.5. Then this part will become negative, the under root part will become negative, and this whole part will be an imaginary number. So this equation will have real part and an imaginary part, so you will always get poles like this. The third case is if you put zeta is equals to 0, we'll say we are dealing with the second order system, which is an undamped, which is exhibiting an undamped response. In that case, you will always get 2 imaginary poles. We can plot these poles like this. Otherwise, what you can do, you can just simply put zeta is equals to 0 in these 2 equations. So this term will become 0. This term will become an imaginary number. The same thing will happen with this equation. This term will become 0 and you will get an imaginary number for this part. So a positive imaginary number and a negative imaginary number. So if you draw these 2 numbers on the S plane, you will always get poles on the imaginary axis like this. The fourth and the last case is the critically damped. Say for example, if we put zeta is equals to 1 in these 2 equations, we will always get 2 real but equal poles like this. So these are actually 2 poles that are on the same point. So we'll say a system is a critically damped system if zeta is equals to 1. Now these shaded regions, they are actually exhibiting that which part of the S-plane is considered as underdamped, overdamped or critically damped and undamped. Let us say for example, just by looking into the S-plane, if your poles lie in this region or in this region, you will say you are dealing with an underdamped system. If your poles lie on the negative real axis, you can simply say the system that we are dealing with is an overdamped system or it may be a critically damped system. Similarly, if your poles lie on the imaginary axis, whether positive or negative, you will say the system that you are dealing with is an undamped system. If your poles lie on the right hand side of this S-plane, it simply means that that is an unstable system. This is another graphical representation of what do we mean by damping. Say for example, this is your S-plane, this is your unstable region. This is a negative real axis and this is your positive and negative imaginary axis. Now, if you start moving towards imaginary axis, whether positive or negative, you will have less damping in your system. And if you start moving towards negative real axis, you will have more and more damping in your system. This is another depiction of how the response of your system will look like if you have poles in underdamped region of your S-plane, overdamped or critically damped system, or if you have an unstable system having poles having imaginary or real poles. Let us say for example you are dealing with an underdamped system having two equal and opposite places. One pole is at here and the other pole is here. So you will always get this kind of response, system response having oscillations which will die out as you move along the time axis. Now, if you have a system whose poles lie on the negative real axis, you will always get this kind of response having no oscillations. Similarly, in the unstable region, the opposite happens. Now, this was a stable system because it was approaching zero, it was moving towards convergence. But if you are dealing with an unstable system, the oscillations starts increasing. And the same thing happens with this positive real axis part where you will get increasing exponential graph approaching infinity. What is damping? This is a very simple example I have given here which is related to a swing. Let us just read out what this example says. James went to the playground with his friends one day, and when he got there, he saw his favorite piece of playground equipment, the swings. He ran to the nearest swing, sat down, pushed off the ground, and then pumped his legs back and forth to make the swing go higher and higher. Although he might not have realized it, James was causing the swing to exhibit oscillatory motion. So he was actually going backward and in the forward direction. What would happen if James suddenly decided to stop pumping his legs as he was swinging? Would his swing just keep on oscillating forever? Would it immediately stop moving? Instead, the amplitude of the swing's oscillations would slowly begin to decrease rather than stopping at once. Although, after James stopped pumping his legs, the swing is still oscillating, but the oscillations are damped, or you can say that the oscillations the amplitude of the oscillations will start decreasing, which means that there is some force that is causing them to become smaller and smaller over time. In this case, the force that is responsible for this damping is probably friction with the air as James and the swing move back and forth. Now, if you start drawing the to and fro motion of James, then you will get a graph like this, where you start with the maximum amplitude, and as the James stop pumping his legs, the amplitude of the oscillations is decreasing along the time axis. So in simple words, we can say that damping is something which restrains vibratory motion. The vibratory motion can be mechanical oscillations, noise, and alternating electric currents, or anything else. So we have already discussed that based on the value of zeta, we can define a second order system as overdamped if zeta is greater than 1, critically damped if zeta is equals to 0, or underdamped if zeta is greater than equals to 0 and less than 1. Or if zeta is equals to 0, that is an undamped system. The response of the second order system to a unit step input can be like this. If you are dealing with an overdamped system, you will always get a response like this, having no oscillation. So this is actually the unit step response of your second order system. This is your unit step signal that you have applied at the input of your second order system, and this is the output response that you are getting. If your system is overdamped, you will get a response like this dotted red line, having no oscillations. Now, if you are dealing with a critically damped system, then you will get a response like this black dotted line. So this is actually the limit. After that, your system will enter into an underdamped state, and you will see oscillations in your system's response. So based on the system's responses, you can easily identify whether you are dealing with an underdamped system, critically damped system, or overdamped system. Let us say that we want to find out certain parameters in the system's step response. If you are dealing with an underdamped system, then zeta will be greater than 0 and less than 1. Omega n will always be greater than 0. The second order system response due to a unit step input will look like this. Now here we have identified certain things. Say for example, if you are starting from 0, then there is a time delay factor, which is the time required for the response to reach half of the final value the very first time. So the time from 0 till this 50% of the final value is your delay time. Then rise time, which is mentioned here. The rise time is the time required for the system response to rise from either 10 to 90%, 5% to 95%, or 0 to 100% of its final value. However, in this graph, we have marked rise time from 0 to 100%. Usually for an underdamped second order system, the 0 to 100% rise time is normally used, and for overdamped system, the 10% to 90% rise time is commonly used. You should keep these things in your mind that if I say find out the rise time if you have an overdamped system, which means that you will always start from 0.1 and you'll end at 0.9 here, and you will take out the difference between these 2 points on the time axis, and that will be your rise time in overdamped case. The underdamped case is already mentioned here. Then we have peak time. Okay, so this is another representation of the second order system response. Here we'll find out what is peak time. Peak time is the time required for the response to reach the first peak of the maximum overshoot. So the peak time is actually mentioned here. So this is your peak time. From here to here, this is your peak time. Then you have the settling time. It is the time required for the response to reach the steady state and stay within the specified tolerance bands around the final value. In general, the tolerance bands are 2% or 5%. So this is your final value. Whenever this second order system response reach within 2% or 5% of the final value, you will say this is your settling time. So we have marked 5% settling time by these dotted lines, as you can see here. So this is the point where our system response is actually coming within 5% of the tolerance band. So the time from 0 till this part is our settling time. The maximum overshoot is this time. The value of your system response greater than the final value. Now this is your final value. Whatever the value above this point, that will contribute to the maximum overshoot, which is marked by A here. This is your S-plane. The location of the poles on S-plane can be used to find out lots of things. Let us just see what we can find out from the location of the poles on S-plane. Assume we are dealing with an underdamped system having 2 poles. One is located here and another one is located here. So if you draw a straight line from the origin to this pole, then it will be your undamped natural frequency. If we look at this S-plane where we have drawn a circle, so you have a pole at 3, then here and then here. So it means that on the circumference of the circle, the natural undamped frequency would be 3 radians per second in this S-plane. Even if you are talking about this pole, then if you want to find out the undamped natural frequency, you just simply have to draw a line from 0 till this point, and that will be your natural frequency. Based on this, we can simply say an S-plane is divided into constant natural undamped frequency circles. You have this smaller circle here, so it means that that is a circle having a very small natural frequency. Now if you draw a bigger circle around this circle, so it means that that is a system having a natural frequency which is larger than this system. And if you draw another circle which is encircling these 2 circles, you can simply say this circle system response is having a natural frequency which is bigger than these 2 systems. The second thing that we can find out from the pole 0 plot in the S-plane is the damping ratio. It is simply the cosine of the angle between the vector connecting the origin to the pole and the negative real axis. That is this angle theta. Zeta is simply equals to cos of theta. So if you know the value of this theta, by putting this value in this equation, you can find out the value of zeta here. The other thing that we can deduce from the S-plane or the pole zero plot on the S-plane is that based on the value of theta, you can find out whether your system is underdamped, critically damped, or overdamped. For this, you simply have to divide your S-plane into 90-degree angle. That is, assume this x-axis is your 0-degree line and this y-axis or imaginary axis is your 90-degree line. Now we always, whenever we will be talking about the pole values or underdamped systems, it means that we always have to talk about the poles that lie on the left hand side. Only then you will be talking about a stable system. We will not be dealing with poles that lie on the right hand side because that is an unstable system. So that is your 0-degree line and that is your 90-degree line. So if the theta value lie between 0 and 90 degree, between the negative real axis and the positive imaginary axis, and the negative real axis and negative imaginary axis, it means that your theta is between 0 and 90 degree here, 0 and 90 degree here. This also means that your poles will either lie in this axis or in this axis. In that case, your system will be an underdamped system because if you put the value of theta between 0 to 90 degree in this equation, you will always get zeta between 0 and 1, which means that your system is an underdamped system. The other case is theta is equals to 90 degree. If you put theta is equals to 90 degree in this equation, you will get zeta is equals to 0. Which means that you are dealing with poles which lie on the imaginary axis and your system will be an undamped system. Thirdly, if theta is equals to 0 degree, it means that you will always get zeta either greater than or equals to 1 and your poles will lie on this negative real axis and your system will either be an overdamped system or critically damped system. Okay, let us solve an example of finding out 0 from this S-plane pole graph. You have this vector line connecting the origin to this P point. Now this is your pole. What you simply have to do, you just have to find out what is the value of theta in this S-plane. In this case, it is 45 degree. So in order to find out the value of zeta, we need to use the previously given equation, which is zeta is equals to cos of theta. So in place of theta, we are putting 45 degree angle and we are coming up with a zeta value of 0.707. Okay, another interesting thing to note here is that whatever the pole value is along this line, your angle will remain same and your zeta will also remain same. So it means that S-plane is divided into sections of constant damping ratio lines. Okay, let's solve an example related to finding out the value of natural frequency omega n and zeta. We have this pole plot. Okay, this is an interesting plot because in this plot you have this right hand side axis, a left hand side axis, and this bottom and upper axis. Now what these axes are telling you, and then we have these hollow lines connecting to certain numbers and this sliding lines connecting to certain numbers as well. So let us just simply find out what these numbers are telling us in this graph. This right hand side vertical axis is actually the values of omega n, and this upper and bottom numbers and this left hand side vertical axis, they are actually the values of zeta. So how do we find out omega n and zeta from this graph? Say for example you have these two poles, one is here and one is here. So since these two poles, they are lying between 0 and 90 degree, it means that your system is an underdamped system. Okay, let us find out the cross section of this pole. This pole is actually connecting to this number. If you move like this, and connecting to this number if you go like this. Now this is your omega n value, okay, and this is your zeta value. So in this case your omega n is 2 radians per second and your damping ratio is 0.5. So I think if a question is given to you on this graph, you can easily find out the value of omega n and zeta here. And simply by putting the value of zeta and omega n in the generic form of a second order system, you can find out the transfer function for this system. Then you have an other example. You need to solve this by yourself and you have to find the value of omega n and zeta from this graph. And here you have another example. I think it is quite easy to find out the value of omega n and zeta from this graph. Okay, I'll quickly explain this graph. Now here is your pole value. So in order to find out the value of omega n and zeta, you simply need to find out where this pole is connecting to this line and to this line. Here it is actually cross-sectioning somewhere here. So in this case your omega n will be somewhere about 2.3, and if you go towards this line, then your zeta may be equals to somewhere around 0.48. I think you can easily find out from this graph the value of zeta and omega n. Then you can also solve this example as well and find out what is the value of omega n and zeta.